Imagine waking up to a familiar sunrise, only to watch a massive, deep red dwarf star crest the horizon right behind our yellow sun. The immediate optical effect on the surface is jarring. Every object casts two distinct shadows with contrasting sharpness and color temperatures. You would see one crisp, blue-tinted shadow cast by the hotter star, alongside a soft, blood-red smear cast by the cooler red dwarf. The convergence of two distinct stellar fields creates a high-heat, highly irradiated gauntlet. This proximity triggers an immediate and escalating atmospheric crisis. The first threat comes from the sky itself. The planet is bombarded by a compounded barrage of ultraviolet and X-ray radiation from two stellar sources. This diagram shows a process called hydrodynamic blow-off. Hydrodynamic blow-off occurs when intense stellar radiation superheats a planet's upper atmosphere until it rapidly expands, and the sheer physical pressure of the starlight pushes that gas directly into space. Zooming into the boundary layer, we can see the chemical collapse. A 50% increase in UV irradiance catalyzes the breakdown of ozone, protective molecules made of 3 oxygen atoms, into standard 2-atom oxygen. This triggers a destructive feedback loop. Thinner ozone allows more radiation to penetrate, which then destroys the remaining atmospheric shield. Without that filtration, lethal UVC and UVB rays strike the ground. These specific high-energy wavelengths carry enough power to tear apart cellular DNA and completely destroy vital proteins in unprotected organisms. In a matter of geological minutes, the planet is stripped of its primary chemical defense, leaving the surface fully exposed as a sprawling radiation zone. Even if the atmosphere somehow holds, the physical rotation of the planet offers no relief. The complex orbital mechanics of a binary system completely erase the concept of a standard 24-hour day. During a specific orbital phase known as a double dawn, both stars rise over the horizon in tandem. This drives a sudden, intense spike in both surface temperature and visible light. Later in the orbit, the planet enters a half-night. One sun sets, but the secondary star remains locked in the sky. The landscape experiences a night that is as bright as a typical Earth afternoon, cast in an entirely different spectral tint. Biological life relies on predictable light cycles to function. This erratic schedule triggers a complete collapse of circadian rhythms, the internal biological clocks that organisms use to regulate sleep, maintain immunity, and manage cellular metabolism. Deprived of a reliable cycle of light and dark, organisms cannot anticipate environmental changes. Life is forced into a state of permanent, stressful, arrhythmic survival. Beyond the daily chaos of light, the gravitational tug-of-war between the two stars physically warps the planet's orbit, driving devastating long-term climate shifts. This vector graphic illustrates highly accelerated Milankovitch cycles. Milankovitch cycles are the periodic shifts in a planet's orbital shape and axial tilt that dictate long-term climate patterns. Here, the gravitational pull of the secondary star violently stretches a circular orbit into an extreme oval over just a few thousand years. Looking at the temperature overlay on this same diagram, you can see the resulting superseasons. As the planet is pulled further away, thick ice belts form across the equator. As it is violently yanked back toward the stellar heat, those ice caps melt into global deserts. This constant gravitational stretching also affects the planet's interior. The competing fields physically flex and grind the crust, a process called tidal heating. This friction generates immense internal heat, triggering global geological volatility and massive volcanism. The planet is caught in a vice. It is cooked from above by overlapping radiation fields and stretched, frozen, and fractured from within by the relentless pull of two gravity wells. If an ecosystem manages to survive these conditions over millions of years, the resulting flora would look nothing like what we see on Earth. Earth's plants are green because chlorophyll specifically absorbs blue and red light while reflecting green. But in a binary system, a massive portion of the available light comes from the low-energy infrared spectrum of a red dwarf companion. Green pigments would starve. Alien vegetation would evolve to be pitch black or gray. This mutation allows the flora to absorb every single available photon across both the visible and near-infrared spectrums, maximizing energy intake from a dim red sun. These dark plants also have to manage immense heat stress. They would develop a complex vegetation red edge, a specific biological mechanism that abruptly reflects certain infrared wavelengths to prevent the plant from overheating. They would need to precisely tune this reflection to the unique thermal output of both stars. Nature discards the familiar green canopy entirely. It replaces it with a shadowy, light-devouring biosphere specifically optimized for a hostile and shifting spectrum. For advanced life, or hypothetical human colonists, adapting biologically would take too long. They would have to engineer their survival against the relentless UV flares and cosmic radiation raining down on the surface. This requires abandoning the surface. Colonists would build subterranean architecture, constructing their cities deep inside natural lava tubes or beneath meters of dense regolith to block the cosmic bombardment. They would rely on hydraulic shielding. By lining the colony walls with thick water tanks, they utilize the hydrogen atoms in the water as a highly effective physical barrier against incoming cosmic rays. On a planetary scale, they might attempt stratospheric aerosol injection. This is a massive geoengineering strategy where highly reflective particles are deliberately dispersed into the upper atmosphere to bounce a portion of the dual sunlight back into space, artificially cooling the world. The binary star system functions as a cosmic crucible. Its brutal physical laws force life to become tougher, weirder, and darker, just to survive under two suns.